welcome to today's session of Saturday Talk by JanyuTech. Today we have Professor Dr. Aditya Paranjape to deliver today's session. Professor Dr. Aditya Paranjape received his PhD in Aerospace Engineering from the University of Illinois in Urbana-Champaign in the year 2011. He is currently Associate Professor of Mechanical and Aerospace Engineering at Monash University in Australia. Prior to this, he was a Senior Scientist at Tata Consultancy Services TCS Research. He is also an Honorary Lecturer at Imperial College London and visiting Associate Professor at IIT Bombay. His research interests are centered around flight dynamics, control systems, and multi-agent systems. Today he is going to speak on the modeling and control of multi-agent systems, principles, and experiences. Over to you, Professor Paranjape. Thank you.
Thank you very much for the introduction, and it's a pleasure to talk to everyone. I usually join these talks. It's a very instructive series, and kind of having seen some of the previous speakers, I hope this talk is not going to be a letdown. All right. So here's a very brief outline. I suppose some of you are familiar with the notion of multi-agent systems. I don't know how many of you work formally in that space. So I thought I should maybe start off with a little bit of a taxonomy, because occasionally we hear these phrases, but it's sometimes good to know what they mean, maybe in slightly more precise terms and the kind of problems that are involved. And then I'll jump straight into a few examples which are drawn from my own previous work, and also hopefully tell you a little bit about what kind of avenues exist along which these areas can be developed. So the work I'm going to show you today would not have been possible without some fairly good collaborations that I've been fortunate enough to have. So Sunjo Chung at Caltech was my PhD advisor. He's also a collaborator of mine. Some work I'm going to show you today was done with Professor David Shim at KAIST, Professor PB Sujit at IISER Bhopal. At TCS, I worked with Taufik Bharat, Vinay Kulkarni, Anvesha Basu. Okay, so here's a very quick outline of the talk. So I start by giving you a bit of a taxonomy of multi-agent systems, and the idea is for those of you who maybe don't work in that space, it's good to know how certain terms or certain concepts are used in multi-agent systems. And then by way of examples, we'll jump into how systems are modeled, what kind of control problems arise, and all of these problems have come up at some point of time. Most of them in my research, but also some in, as you'll see, in practical circumstances as well. And so again, as an acknowledgement, I want to thank all of the collaborators I've listed here, because it was working with them that actually made all of those results I'm going to show you possible. So wouldn't have been feasible without them. Okay, so let's go to the next slide. Bhushan, okay. All right. So this is where we were about what an agent is. And so as you said, an agent is either a physical entity for those of us who work in robotics and such. And that entity has some internal state, as I told you, position, velocity. There are rules for state transition. So Newton's laws in the case of mobile robots. You have sensors to perceive the environment, to communicate with other robots, and you have actuators, to change the state, but also to interact with the environment directly. Now, interestingly, like I said, I spent 5 years at TCS, and one thing I picked up at TCS from my colleagues was how they view these concepts in a software domain. And while it's a different domain, the reason why the software side is interesting is because that's the way in which actually gets coded out. So it's good for us to know what an agent is. So in computer science, and by the some of you are probably experts in this space, so hopefully I wouldn't make a pig's breakfast of this definition, but it's an object. Sometimes it's also a thread, and that's endowed with a memory, which is the equivalent of a state in a physical system. There are behavioral rules or rules for state transition. There is an inbox which allows you to receive messages, and you have a protocol to pass messages to the other agents. And there is one concept which you don't find in physical systems, which is that any agent in the software world can spawn a new agent. So you can't destroy agents as such, but you can create a new agent. You don't usually see this in the physical world, but here it exists. So what you see on the right are just two pictures showing two examples. The first one is a connected system consisting of combat vehicles. The other is a simulation environment showing urban traffic. And in the urban traffic example in particular, you would actually use all of these computer science oriented definitions to represent what are actually fairly physical objects. All right. So with that idea of an agent, so let's move to the next slide, please. All right. You may just need to scroll down. I can only see the title of that slide. Okay, yeah. Okay, so very often we hear multiple words used in the context of multi-agent systems. You'll hear words like teams or swarms, formations, and the like. But what it fundamentally is two things. There are swarms where every agent has fairly simple behavioral rules. There is no notion of a global goal. There are just rules for what an agent does locally. And whatever happens globally emerges from these local interactions. So the phrase emergent behavior is key in the context of swarms, in the absence of a goal. On the other hand, when we talk of a team, what we have is a very well-defined notion of an individual goal. and it's clear that every agent basically seeks to maximize their own individual goal. There might also be a global goal, in which case these agents can decompose that global goal into assignments that individuals can manage. But the key driving factor in a team, unlike a swarm, is goal maximization. So I think as long as we understand these two words, I think it becomes easier to formulate and solve problems. Traditionally, the distinction between these two has also been made in terms of the fact that swarms typically tend to be large. I mean, in the sense that there are lots of agents in there. This is a concept that we'll get to visit in just a few minutes from now. Whereas teams are very compact, agents are specialized, and in that sense is where people tend to distinguish between teams and swarms. However, even if you use that notion, you find that really it comes down to goal-driven behavior in teams and just local behavioral rules in swarms, not driven by any particular goal. Okay, let's go to the next slide. All right, I think, yeah, well, wait. Okay. A few more common terms that you'll always hear is you'll hear terms like communication graphs or network topology. We won't have a chance, unfortunately, to see it today, but that's a view in which you don't just model agents just in terms of their behavior, like we do with swarms, or in terms of some goal-seeking behavior as we do with teams, but you literally model them as nodes on a graph, and you try and understand how they interact and what it does to the graph on the whole, and how that graphical structure in turn affects the stability of the system, for example, on the whole. That's a graph theoretic view. That's a fairly dominant view in multi-agent systems literature, but today we'll not get into that side at all. But this is just something that you have to know if you decide to get into this. You'll also look at behaviors which are either cooperative or competitive. I think that definition is fairly self-explanatory, but what it basically means is in cooperative problems, the strategy that every individual takes is coordinated in some sense towards the global goal. Whereas when the behavior is competitive, the understanding is if you are an agent that's trying to decide your strategy, then the outcome of that strategy in terms of your goal is also impacted by the strategy taken by the other agent. And consequently, when you try and optimize your strategy, the understanding is that you're going to assume some model for the other agents. And that's what we mean by competitive. It's just the fact that your strategy is a function of how you model the strategy that the other agents use as well. Some more terms that you hear occasionally in this setting, you have problems that are centralized and at one extreme, which is where all of your computation, all of your decision making happens at one node, and at the other end you have distributed systems where there is no a single global oracle that sends out information. Everything gets done locally, and simply what the mass does emerges locally, not locally, but it just emerges from those local interactions. So those are called distributed systems. And in the middle, you have decentralized systems. Now, sometimes decentralized and distributed are used synonymously, but there's a subtle difference there. In decentralized systems, you still have an oracle that just partitions tasks between the multiple components of your system. So that's just sort of setting out the nomenclature. And what I've listed then are a bunch of typical problems that you encounter in the space of multi-agent systems. At this point, these are names, but the ones that you see there listed in green are ones that we will go through today, just by way of some examples. I don't think I want to read that list out. Let's just go to the next slide and we'll start looking at these examples. And for each example, the way I'll do it is I'll talk about some principles that have gone in, and then I'll tell you where it got applied. Because thankfully, for a lot of the work I've done, I've been able to find some other application that's been of interest outside of the regular academic circles. So hopefully I have a chance to tell you about that as well. So the first example I'm going to show you is that of robotic herding. This work started back in 2013. This was in the aftermath of the US Airways 1549 crash on the Hudson. So that iconic photo on the right really doesn't need any further introduction. But what was very clear at that point was something had to be done about the fact that a large number of man-made systems were now directly in conflict with birds, also with ground-based animals as such, but birds were a fairly serious problem. So airplanes, wind turbines are of particular interest. And what's traditionally done, if some of you even go to the airport in Mumbai or any of the other cities, you'll occasionally find them firing smoke guns in the air. You'll find them blowing loud horns. That's the way they scare birds away. But the fact is, when you use smoke guns or horns, the fact is that the birds have already intruded the airspace around the airport. Scaring them after that probably is only half as effective as it would be if you could keep them out of the airspace. And that's where this robotic falcon that you see in the middle comes in handy. So this robotic falcon was developed, I believe, for the first time in the Netherlands. It's remotely operated by a human, and it has been shown to have some amount of success in keeping small birds away from airports. eventually, long-term studies, I believe, have yet to be done. But considering that it is used, it's probably some indirect evidence that maybe it is effective with birds over several years. And although birds do have memory and they do pass on information to their kin and to their succeeding generations, it looks like this knowledge hasn't probably gone across as rapidly as we would have expected. So there is some effectiveness in this robotic falcon. Now, what we were interested in at that point was taking this robotic falcon, or a similar concept really, from something that's remotely operated to something that is fully autonomous. And if you have to make it autonomous, you have to first start by modeling the behavior of bird flocks, figure out how this robotic falcon can interact with those flocks. And once you model the interaction, it then becomes a control problem to figure out how to keep flocks away. So can we go to the next slide? Right. So here we, for the first time, enter this idea of how do you model swarms. So broadly for swarms, if you decide to model swarms as a collection of individual particles, then the motion of the individual particles can be described typically using Newton's laws. So, the rate of change of position is velocity, the rate of change of velocity is acceleration. And what you need to really do is figure out how the acceleration of every particle depends on the motion of the other particles in its neighborhood. And what you see here in the white box on the right is something known as the Reynolds model. There's another model known as Cousin's model. I have not been able to tell if the guy is French or whether he's English. His first name is Ian, so probably English. So I don't know. So Cousin's model is an alternative as well. Reynolds model is probably sort of our go-to standard for flocks. And what you notice in the equation on the right, the first equation is just the rate of change of position is velocity, not of interest. The second equation contains the acceleration terms. And those three terms on the right, three sets of terms rather, are put in colored boxes. And if you look to the left now, you will see what those boxes mean. The blue box, for example, is the attraction repulsion box. So those terms, which are position dependent, essentially keep all birds at a constant distance, which here is r safe from the birds in their neighborhood. Now, there's no way to control how many birds you have in a neighborhood. It could be 3, it could be 4. But no matter how many you have, you'll always stay at a distance r safe from them. The yellow terms achieve velocity alignment, and that's why flocks actually move in the same direction. There's one term that aligns the velocity between the neighboring agents, and there's one term that gives every agent in the flock some global reference. And that's effectively what you see in migratory birds. They want to, if you're looking at migratory birds and you intercept them somewhere in between, you will just want to you'll see that they just know what direction they want to fly in. That's what the second yellow term does. And that last term, which is shown in the red box, is of interest to us because that term captures how every agent in that flock responds to a potentially hostile agent from outside or from a bird of prey. So so this model was fairly straightforward, but as it happens, there is almost no data out there to actually get those parameters that you see out here. This KR, KV, KG, KP, those terms are completely unknown. And at this point, the only way to get them is to take drones or take birds of prey, get them to fly close to the birds that you're interested in herding and experimentally extract some of those parameters. Now, what I was going to show you on the next slide, but in the PDF, I don't know if it has appeared. Is there a video there that you can play? Okay, probably not. Okay, so had this video played, and I'm sorry about this, what you would have seen was a series of experiments that we conducted in South Korea. They were conducted by Professor David Shim and his group. And we actually flew small quadrotors close to two different families of birds. The first family of birds was called egrets. Second family, I believe, was that of loons. And we actually made an attempt to fit some of the parameters from the Reynolds model that I just showed you earlier using data from these engagements with the birds. What was interesting was it seemed to work fairly well with the egrets, at least with the experiment that we did. With the loons, when we interacted with them, we thought we were interacting with a single flock of birds. But suddenly the whole flock started to break apart, and what we realized was it wasn't a single flock. It was actually a collection of flocks. And that's yeah, this is Chung Lab. Yeah, if it's on YouTube, yeah, you'll be able to find it. You can actually just jump ahead because there's a lot of other stuff in this video which may not be of interest. Yeah, Bhushan, that's all the algorithm. I think what you should do is just jump to about 30 odd seconds in. Just play from 39 seconds. Yeah. Okay, great. So that's the first thing you will see. So in this video, I can't show you. I can't move my mouse around. But yeah, look. We've annotated the video. So we had a little drone out there, and as birds approached, we flew the drone. And this was manually flown close to the birds just to see how the birds would deflect. And what we wanted, and remember, by the way, this may look very obvious, but when you create these models, it's not even clear if the birds would literally get deflected, just like two charged particles get deflected if they're of the same parity. But they did. The birds didn't do anything unexpected. Like what we were expecting was, in the worst case, you might see some 3D maneuvering, or you may see some birds taking very aggressive turns. None of that happened. And because it didn't happen, we could actually fit parameters pretty well. In the second video, you have a whole bunch of incoming birds that are shown in that red circle. But you'll very soon see a graph. Now, these birds change direction as a whole, as we expect, but it's not enough to just get that change in direction qualitatively. We do want to fit parameters to it. And when you try and fit parameters, you realize that whole collection of birds, collective, isn't a single flock. It's actually a collection of flocks. And all those individual flocks actually have slightly different constants. And that was actually quite fascinating because we didn't know exactly how to deal with it. We realized it's a challenge, but from there on, the project wasn't continued. But that's a very interesting herding application that we started off with. We eventually ended up patenting this system as well. So we just got it patent, I think, a year or two ago. And at this point, I'm very interested in looking for applications. So if Janyu, for example, is interested in developing something like this, which we can use to protect our wind farms in India or offshore, be very happy to work on this technology. Okay, now what we are doing now, moving on from the herding problem, is we're now trying to see how we can model large swarms using some formal methods called mean field methods. So the intuition is that if your swarm is large, the number of agents should not matter. So that equation that we wrote earlier, Reynolds equation, requires that you write one equation for every bird. And we know that intuitively it's not needed. So if it's not needed intuitively, how do you convert that intuition into mathematics? And it turns out the way to do that is to write out aggregate equations. And you can either write ordinary differential equations if the number of states you're interested in is finite, which I'll show you just via an example. Or if in the case of birds, for example, what you end up with is a partial differential equation known as the Fokker-Planck equation, which is just a version of the well-known continuity equation from mechanics to describe how the flocks evolve. The key is they don't describe the state of individual birds. Instead, what those equations try to describe, both of these, is how the distribution of the birds or the agents in general changes across the state space. So you lose track of individual birds, but you get to know exactly what fraction rather of birds or what ratio of birds exist within a certain part of the state space. So since I've told you about this, let me go to the second example now, where you will see this principle in action. So if you go to the next slide, the second example deals with our work on COVID-19, and this was with my colleagues at TCS. This work had two components. There was one, if you go to the next slide again, Bhushan. Yeah, so there were two threads that we followed here. The first one was an agent-based model. So this was so that agent-based model is literally a multi-agent system. You have we modeled. Every agent in our system was either an individual or a family in some cases. It could be a physical place in Pune. It could represent a vehicle where people could drive or take a cab, for example. And we also use them to represent virus particles. So you see the whole diversity of agents being represented in this system. For computational purposes, we were limited to about 50,000 agents at a time. So we were limited to running our simulation for one ward of Pune at a time instead of running it for the whole city. Now, the state of every agent depended on what that agent was. So if it was an individual, for example, the state was where the individual was located, what state the individual was in vis-a-vis COVID. So were they susceptible, were they infected, were they vaccinated, and so on. And then depending on how the individuals interacted with other individuals, we had state transition rules. So if two people met and they were both non-infected, nothing would happen. If one was infected, they persisted, they sort of stayed together for a certain fraction of time, then there's a certain probability we would change the state of the susceptible person to exposed, and so on. So those were the behavioral rules in the system. Now we realized very quickly that the big challenge when you write out systems like these, although they look very nice, it's that you have to set the initial condition correctly, and that's extremely hard. It took so my colleague Shouvik Bharat from TCS, it took him several weeks working with epidemiologists to figure out how to seed these models. So it was no mean feat to do this. But once you get it, you get a model that's very realistic, because you're modeling little things like cars, you're modeling people. You can model interventions at that level of detail as well. So you can say, for example, during a certain time of the day, cars are not allowed, and that's it. Those agents are disabled for that period. And while this model is extremely powerful, it's also fairly cumbersome to run. For some cases, you may not even need to run the model, and what you instead use are aggregate models or coarse-grained models, as they're called. So these are sometimes referred to as SIR models. And it's the same idea that, if I'm trying to model an epidemic, and I don't particularly care about maybe sort of studying very low-level interventions, then maybe all that matters is how many people or what fraction of the population is infected at any given time, what fraction of the population is vaccinated, and so on. And then you just assume that there are some rules for how people can mix. And when you do that, you get equations such as the one that's shown in the box on the right hand side. That's an equation which tells you how people move from being susceptible to being infected. And when I say people move, I mean how the fraction of people that are susceptible, how that fraction changes to a fraction that's infected, and so on. One thing that we realized here was, especially with COVID, is that because people would stay in a certain bracket, like let's say the exposed bracket, for a prolonged period of time, you had to keep track of to add those extra states to the system. But otherwise, it was fundamentally an SIR model that we wrote out. Now, all of this was perfectly fine, but now let me show you what happened with the case study, because that was, I think, as I say, when rubber meets the road, that's actually what happened. Can we go to the next slide? We'll just skip this slide for now. We don't need this right now because I've already gone over it. Yeah. So with Pune, we were fortunate at that point to be able to work with the Pune administration. And again, I think it's to the credit of the team, especially Shobik and the epidemiologists, that the models were good enough that when Pune unlocked, starting late June, I believe, the unlocking process was done in consultation with the team from TCS. So there were several meetings that we had with the district commissioner, and they would ask us, can we, for example, open shops on one side of the street and not the other? Can we keep shops open on the weekdays but not the weekends? And because we had the APM, we could actually answer those questions in that level of detail, which was great. And we published the first set of results in October 2020. And one thing we predicted was that there would be a second wave sometime in early 2021, depending on what the government did during December and January in that period. So if they unlocked in December, we thought it would be in February. If the unlock was completed by January, that wave would probably happen in March. Now, as it turns out, in March, the cases started to go up. And if you just look at the plot below, I'll come to that plot in just a minute or so, but you'll see those black points which show the actual case numbers. When they started to go up, we sort of had an internal discussion, and we said, look, if the cases go up and the government panics, then we'll probably have a lockdown. And we don't need anything quite as harsh as that, because we've predicted a second wave. That wave's not going to be as intense as the first wave. We have the medical infrastructure to deal with it, so we'll be okay. What we did not know at that time was that there was a new variant in the mix, namely the Delta variant. And as it turns out, that the variant was identified and labeled as a variant of concern only in mid-May. So as we started running scenarios using the ABM, the agent-based model, we saw very rapidly that there was a divergence between what we were predicting and what was happening on the ground. And at that point, some amount of confirmation bias kicked in, and we tried to explain that away by saying that, look, maybe we haven't modeled the mixing correctly. Maybe people are violating the norms, no one's following the rules, and so on. But interestingly, because we had that second SIR model, it's a very aggregate model. It can be run in a matter of seconds on a decent laptop. I remember we were in a meeting with the district commissioner, and I ran the SIR model, and I told the guy sitting next to me, it looks like we are the dynamics are nothing like what would happen if people were just not following the rules. Something very weird is happening here. But because we were all taken in by the ABM that we had in our midst, we were like, no, this is probably wrong. That's not what's going on. And so there we actually missed an opportunity. So the lesson that we learned from the experience was, okay, ABMs are great. You do need them to answer very low level questions. But equally, if at some point you need to run a rapid sanity check, a rapid verification, you also need those aggregate models. They have their own value. They're not much more valuable than that. You can never supplant an ABM. But for rapid verification, you need those SIR models. And in situations like these, where it looks like something has changed dramatically on the ground, it's always good to start with the coarse-grained models, get some number on what's happening in at the level of mixing, for example, and then move to the ABM and figure out what's going on in terms of people's behavior, right? And what we also appreciated was, well, if an epidemic were to happen again, and of course we hope to God that nothing of this not happens again, well, how do we deal with the confirmation bias? The thing with ABMs is because they are so complex and you've spent so much time tuning them and validating them against data on the ground, you are inclined to believe that they are right. And then if something starts to go haywire, one of the assumptions starts to go haywire, well, what's the signal for us to retune? So that's a lesson that we took back from this experience with COVID. But I think COVID was a fine example of, you seeing the whole gamut of multi-agent models coming into play and actually having some impact on the ground. All right. Coming close to the end now. Can you go to the next slide? Yeah, so that's actually the work I'm doing at this point. And the setting that we've created is we have agents that are greedy. And what I mean by greedy is the following. If you look at that figure on the right, the first figure on the right, you see a space, the hexagon, that needs to be covered by 4 robots. You have one robot that enters the system first. It's followed by the second robot. Now, the 2 robots realize that it's just the 2 of them in that space, so they partake 50% of the space each. That's what we mean by greedy. They don't take any more than 50%. Okay, when the third robot enters the picture, that third robot only meets one of the two robots. So the robot that it meets, let's say the robot at the bottom, robot number 3 and robot at the bottom take up only 1/3 of the space each. That first robot still doing 50% because it doesn't know that robot number 3 has entered the picture. And this goes on as more and more robots get added, they start partitioning the space. Now the question for us was, as these robots get added and they interact, is there a possibility that coverage can be lost because some robots behave greedily and don't realize that some part of the space is uncovered? And this was where one of my students actually did a really nice bit of work. So we said, instead of looking at some random space, let's look at circles. They're the simplest environments to work with. And a plane circle is geometrically not very different from a disk. It's the same problem. And what we realized was, if the number of robots is 4 or less, then no matter what you do, you will guarantee coverage 100%. But the moment the number exceeds 4, things go for a toss. It becomes very sensitive to how the robots interact. And I think this was one of the first set of results where it became clear that coverage doesn't just depend on the scale of the system, as it were. It depends on the number of agents. That idea that things can behave differently when you go from 5 robots to 6 robots and from 6 to 7 robots, that thinking itself was a little new. So with greedy behavior, we know what happens, and what we are doing now, I have a bunch of students at Monash working on this, and probably a few more might join me in the not too distant future. We're trying to see if we can start off by being a little less greedy at the outset, but as you interact more and more, you can become greedier so that eventually you have a fully equitable partition that's compatible with fully greedy behavior. And that's also practically very useful, because if you partake a larger area, you're going to spend more energy traversing it, which is not worth it. Plus the reliability of response goes down as the distance increases. So you want to keep that region that you're responsible for as compact as possible. Okay, so with that, I'm on my last slide now. Bhushan, you can jump up. So what we've looked at today, I just wanted to introduce you to the world of multi-agent systems. It's a fascinating world. We looked at the taxonomy of that space. We looked at the kind of methods that exist in there. We've seen a bit of modeling now. So we've seen how you create agent-based models. I've shown you a little bit about aggregate models. The whole idea was to signpost you to different things. That's why I used all of those words, Fokker, Planck equation, and so on. It was not to make it sound fancy, but just to tell you where to look if you're interested in that space. There's a graph-based models that I didn't talk about today. It's a fascinating space. I couldn't do any justice to it today. And I showed you a whole classes of problems that exist in this space. They're all of interest, of course. The 4 in greens are the ones that I just showed you. There are 3 more that are maybe a little more contemporary in their relevance. So actuator sensor placement is how do you place sensors in an environment, which is similar to how you distribute communication nodes in a space. Distributed learning is a big thing. It's in fact moving in the direction of some generative agents as well. And the traditional problem of consensus and decision making, when you have a fully distributed system, when you have imperfect communication, that problem is still very much alive. So with that, let me stop. I'm sorry for the trouble that we had at the outset with the slides, but I'm glad we could at least finish in time. So that should leave us some time for questions. Thank you.
You talked about greedy, for example, going from say 4 to 5 robots or 5 to 6 robots, etc. And you said that the complexity significantly increases. So is it possible that there is a challenge with respect to computing limitation? Let us say if you could deploy high performance scalar computing or say quantum computing, etc., that problem could be solved?
No, it's not complexity. It's just that coverage gets lost, and that's a fundamental property of that system. See, when I told that the coverage is lost, it's independently of how it's computed. And what I mean is there is a specific formula for how the space gets assigned to robots, and as long as that formula gets used, you can show that coverage is lost. So it's not a function of the method that you use to compute it. It's the formula. Now, having said that, we are trying to get into the space of figuring out how to solve that problem using learning, because like I said, we ultimately want to be greedy, but ultimately not at the outset. So figuring out that transition from of slightly altruistic to fully greedy, that's something that we are trying to now figure out. And there it might be a computational problem fully. So yes, so not the results that I showed, they are very fundamental in nature, but the problem that we are trying to do now is very much along the lines that you just talked about.
Okay.
By the way, I should also add, Hemant, you worked on these problems, right? I mean, I actually tried finding a video. I didn't have it on this computer. I want to show them. So for those of you who are on the talk, so Hemant was with me at IIT Bombay, and Hemant actually worked on some of these problems so his problem was, how do you allocate a set of robots to a specific formation? And I think, Hemant, you used auction, isn't it, to set up robots on a spiraling pattern?
Hungarian algorithms.
You use Hungarian. Okay, but it's the same problem that you solved, right?
Yes.
Yeah.
I was
Yeah,
just
so I mean,
telling Kishan that when the slide showed the Hungarian algorithm, I was just mentioning it to him that this is the master's project I worked.
Yeah, exactly. Yeah, absolutely. I mean, I still have that video on a different computer, so I have your entire presentation and things. But that's my work computer, so it's somewhere else now. But actually, I wanted to show people. I mean, for those of you who work with Hemant, I mean, he did a brilliant job during those Senate months. I think that was a time when I think you were also trying to set up Janyu. So there were times when you completely disappeared off the radar fully. But yeah, but I must say I'm glad you did, because something really nice came out of it.
So,
Not a lot of people. I have to
we have a nice history, sir. Yeah.
Yeah.
Thanks for
See,
all the
Hemant
support.
disappeared off the radar thanks to Abhimanyu ji, not because of anything else. He was the acting robot there.
Yeah, I still remember
Lot
him
of
from
story.
Jan to March that year. He was off the radar. I sent him 1 or 2 emails. I was like, "ठीक है, चलो," But then he came back saying, "I want to do this." And believe it or not, within I think a month and a half or so, he had that whole application cleaned up. So I was very happy at the end that okay, he had vanished, but he did a fabulous job at the end. So doesn't matter.
I hope I'll improve that, sir.
Oh yeah, certainly.
Sai gives a formal vote of thanks. I should thank you for accepting my request. Actually,
Oh,
आते रहिए sir बीच में. See, our Arun also is our speaker from Madras IIT, and he also talks something which we cannot understand much as business people, right? He is specializing in metaverse. He is specializing in some metaverse and other things. I used to always ask him, can I make a balance sheet out of it? Can I make it into numbers? So, वो चर्चा चलते रहते हैं मेरा और अरुण का बीच में. So keep coming, sir, so that we'll always feel that there is a lot of gap between what we are doing and what we have to do. Because sometimes we also get into a mode of aham, that we are growing, people are respecting us, ये वो उसमें चल जाते. But when I meet people like you, Arun, and other things, we feel that still there is a huge gap between what we are and what we have to do. So that keeps us moving. So I should thank you that you are accepted to be in our Council of Advisors.
Oh no,
And,
it's a
we
privilege to be there. It's a pleasure to be there. I mean,
Right.
look, as academics, we can't do much with technology, right? I mean, we can develop ideas, but we can't take it beyond the point without companies like yours taking the initiative and saying, yeah, we'll take this all the way to the end users. So I think we have to work together. And
Right.
I mean, and honestly, I think and that's what I mean. You should come to us saying, we have a problem with this. Can you help fix it? I mean, that's absolutely what we want to do. Because otherwise, we develop this
Yes.
theory, they get published, but nothing more happens beyond that. Whereas I think I've been fortunate in the sense that a lot of the stuff I've done has made its way down the technology ladder. So, but that's
Yes.
of course thanks to Janyu and some of the other companies that I've had the chance to work with. So absolutely, I mean, it's an absolute privilege to be here. And believe me, if you claim you don't understand the technical side, we don't understand anything in business either. So I think we are both equally blessed with ignorance.
That's